Good morning, everyone. We are starting Unit 1, Lesson 1, Simplifying Polynomial Expressions. So in previous math classes, you would have looked at all kinds of equations, linear equations, quadratic equations, exponential equations. We're going to start by looking at polynomial equations. And the word poly just means multiple, so anything really more than one term is therefore a polynomial expression. In this note, we're going to talk about connecting the factored form of a polynomial to the standard form of a polynomial. So this first graph we have here is what we call a cubic. So this is a cubic. And as we look at the equation in standard form, we'll start talking about why is that a cubic, what makes it a cubic. But just some characteristics to consider when we are looking at a cubic expression. We can talk about the zeros that are on the graph. So the zeros, remember, are where does the graph cross the x-axis. So those are our x-intercepts. And they are located on this graph at -2, 0, and 3. Some other ways that we could describe this graph is in terms of its end behaviors. So we would read this phrase as x approaches infinity. So I'm just going to highlight this. So as x approaches negative infinity, rather. So the arrow is read as approaches, and then we have a minus sign, which represents our negative, and then that sideways 8 is infinity. So as x approaches negative infinity, and what that's talking about is if we look at our graph, as the graph is getting more negative, so it's getting closer to negative infinity, what's happening to our y values? And we can see that as x gets negative, y continues to get negative. So we would say, as x approaches negative infinity, y approaches negative infinity. All right, and then if we wanted to look at x on the positive end, we'd look at this side of the graph. I'm going to use a highlighter. So as x approaches positive infinity, what's happening to our y values? Well, our y's are also getting more positive. So as x approaches positive infinity, y approaches positive infinity. Okay. We can express the form of an equation in many different forms. Factored form is one of them. We would have seen that with quadratics. And now we're going to look at that for higher degree equations like cubics, quartics, and other polynomials. Okay, so we have the factored form, but we could also change this to our standard form. And so when you worked with quadratics in grade 10 and grade 11, we talked about going from factored form to standard form. We have to expand and simplify. So that's what we're going to do in this box. We're going to expand and simplify. So we first have to distribute our 5x inside our brackets. We'll do that first, and then we'll continue expanding from there. So if we distribute that 5x into our bracket, 5x times x is going to be 5x squared, and then 5x times a -3 is -15x, and then we still have that x plus 2. So now that we have two brackets, we call these are a binomial. So whenever we have a binomial times another binomial, because there's two terms in each of those, in order to expand those, we're going to use a process called FOIL, which hopefully most of you remember from previous math class. So FOIL stands for first, outside, inside, last. We're going to multiply our first terms together. So the 5x squared times x is going to be 5x to the power of 3. Our outside terms, so 5x squared times 2 is going to be plus 10x squared. Then our inside terms, so -15x times x is a -15x squared. And finally, we're going to multiply those last terms together. So a -15x times 2 is a -30x. Then we just have to combine any like terms we have in the equation. So right here we have some like terms with our 10x squared and our -15x. So we'll go ahead and combine those. So y will equal 5x cubed, and then 10x squared minus 15x squared is going to be minus 5x squared minus the 30x that was there. Okay, so there you go. We have all these ways that we can describe an equation. And one more thing I want to point out is that I said at the beginning that this was a cubic function, and the cubic part refers to the highest exponent we have on our x variable. So the highest exponent we have in this equation is a 3 on my x. And we always want to list our terms in descending order according to their exponent. So that's why we have the x cubed term first, then the x squared, and then finally the x to the power of 1. Okay, so any equation where our highest exponent is a 3, we're going to call that a cubic. So I'm just going to write here, next to cubic, okay, you're going to have an x to the power of 3. Pause the video here and see if you can fill out the next row of the table for the next graph. So there you go, there's the solution for the next one. We identified our zeros and then we expanded and simplified the factored form of the equation. Just want to mention one more time the end behaviors, because that's something that's pretty new. So once again, as x is approaching negative infinity, so as x is getting more negative, what's happening to y? And in this case, y is getting more negative as well. It's continued to go down. As x is approaching positive infinity, we can see that y is also continuing to get more positive or closer to infinity. So y is approaching positive infinity. Okay, I wanted to take a look at the next example, which this graph is a little bit different. Doesn't look quite like the other one. This graph is what we call a quartic. Looks a little bit different than the cubic, in particular the end behaviors. You can see when we look at the cubic, one end of our end behaviors is pointing down while the other one is pointing up. Whereas in the quartic, both the end behaviors point up. Right? The left side or the left end point is pointing up as well as the right side. So that's just one characteristic different about these types of graph. Let's go ahead and talk about the end behaviors though, or the zeros first. So we have -2. We have a -2 is a 0, -1 is 0, and 3. That's where we're crossing the x-axis. As x is approaching negative infinity, so as x is approaching negative infinity, so the graph is getting closer to negative infinity, what's happening to y now? Looks like as x is getting more negative, y is actually getting more positive. So we would say y, oops, let's just stick with blue, y is approaching positive infinity. And if we look on the positive end or on the right end, so as x is approaching positive infinity, as x is getting more positive, what's happening to y? It looks like y is also continuing to get more positive or approach a positive infinity. The y approaches a positive infinity. All right, connecting the factored form to the standard form, again, we're going to expand and simplify, but we'll have a few more steps here since we have multiple brackets. So I'm going to expand and simplify by distributing this 2x, and then I'm going to go ahead and FOIL the other two brackets so that I'm kind of combining the expanding in one step. So I'm going to first expand the 2x into the bracket, so we have y equals, and then 2x times x is 2x squared. And 2x times a -3 is a -6x. And then I'm going to just change colors here. So then I'm going to FOIL the other two brackets. So first, outside, inside, last, we're going to FOIL those. So x times x is x squared. X times 1 is going to be plus 1x. Our inside terms, 2x. And then our last terms, 2 times 1 is plus 2. We'll simplify anywhere we can before we continue our expanding. So our first brackets, we have 2x squared minus 6x. Nothing to simplify there. But our second ones, we can go ahead and combine that middle term we have there. So it should become x squared, and then 1x plus 2x is 3x plus 2. Now we need to distribute everything from our first bracket into our second bracket. So we have to make sure we multiply all possible combinations there. Okay, so we'll start with that 2x squared. So 2x squared times x squared is going to be 2x to the power of 4. And then 2x squared times a positive 3x is going to be a positive, oops, I wrote that wrong. This has to have a 4 on it. I said it. And then 2x squared times 3x is going to be 6x to the power of 3. And then 2x squared times 2 is going to be 4x squared. Then we have our negative 6x here. We're going to multiply that by everything in the other bracket. So a negative 6x times x squared is going to be a negative 6x to the power of 3. We're just going to have to kind of drop down to the next line. Then we do a negative 6x times a positive 3x. You're going to have a negative 18x squared. And finally, a negative 6x times a positive 2 is a negative 12x. So now we'll try to simplify where we can. Go into the other box a little bit. We have 2x to the power of 4. I don't have any other x4 terms. We look at our power of 3's here. We have 6x to the power of 3 minus 6x to the power of 3. So that's just 0, nothing to do there. And then if we look at our squared terms, we have a positive 4x squared minus 18x squared. So positive 4x minus 18x is going to be a negative 14x squared. And then finally, we have this minus 12x here. Nothing to combine that with, so we can just write minus 12x. And there you go. Lots of expanding and simplifying with that one, but that's your equation in standard form. So you should go ahead and pause the video and try to work through the next example, filling out all of the boxes. Okay, so there's the solution for the next one. Again, this is a quartic function, and the one thing I didn't point out that I would like to, like the cubic function, the highest exponent on our x was a 3. For a quartic function, the highest exponent on our function and equation in standard form is going to be a 4. That's why it's called a quartic. So a quartic's highest exponent is going to be x to the power of 4. So that's just a look at taking our factored form and expanding and simplifying it into the standard form, and then also tying that back to our zeros in our graph. Okay, we are going to review how we simplify these polynomial expressions, just so we know the rules involved. So when we're simplifying polynomial expressions, we want to, when we're multiplying a monomial, okay, we want to make sure we multiply the coefficients, and then don't forget to use those exponent laws when we deal with the exponents on each variable. We're going to use the distributive property to expand or multiply those polynomial expressions. So when we have something like a times, and then in brackets b times c, we're going to take the coefficient on the outside of our brackets, and we're going to multiply it by everything inside of our brackets. Multiply. So a times b is going to be ab plus, so plus over here, a times c is ac. Okay, so that's if we have a monomial outside a set of brackets, we distribute it in by multiplying it. If we have two binomials times each other, so when we have, when we're multiplying binomials, we use a process called FOIL, which you would have seen in past math classes. So FOIL stands for first, outside, inside, and last. So we're going to multiply the first term in each of our brackets together. So x times x is going to be x squared. Then we're going to multiply those outside terms, or outer terms. So you're going to have x times 9, which is 9x. Then the terms on the inside, so the innermost part of both of the brackets, 7 times x is 7x. And finally, the terms that are last in both sets of brackets, which are 7 times 3 in this case, which is 63. And then we just combine any like terms we have, which when we FOIL is always those middle two terms. So we're going to add the 9x and the 7x, and you're going to have 16x plus 63. Okay, so just a little bit of review on the distributive property and FOIL. After expanding the polynomial expression, it may be necessary to simplify by collecting the like terms, which is what we just did. All right, let's look at some examples of this. So when we're multiplying and we have all these terms that are being multiplied together, remember your exponent laws. Our exponent laws say that if we have two powers with the same base, so you can see we have two powers, both the bases are a, what do we do with their exponent? So if we have a to the power of m times a to the power of n, when we multiply those together, we are going to add their exponents. So for this first example, we're going to multiply all of our coefficients together. Our 2 times 3 times a negative 5. For our a terms, when we multiply these together, we're going to keep the base the same, and we're going to add the exponents for our new exponents. So we have an exponent of 1 plus 2 plus 2. And then we have to look and see, what are we multiplying b with? B doesn't have any other b variables in this expression, so we just leave that alone. So if we multiply 2 times 3 is 6, 6 times negative 5 is a negative 30. And then a, we're going to add all those exponents. 1 plus 2 plus 2 is 5. B to the power of 5. So that is multiplied now all out. So if we look at the next expression, we have 4m. And we're going to use that distributive property to distribute it. Don't forget about your exponents. If there's no exponent there, we have an exponent to the power of 1. So 4m times 5m is going to be 20m, and then 1 plus 3 on my exponent, 1 plus 2 on my exponent will be 3. 4 times a negative 3 is going to be a negative 12m, and we add our exponents. 1 plus 1 is 2. And then finally, 4m times 7 is going to be 28m. Okay, expand and simplify the next example. We're going to use FOIL. So first, outer, inner, last. So our first term, x times 3x, is 3x squared. Our outside term, x times 4, is positive 4x. Our inside term is 2 times 3x, which is a positive 6x. And our last term, 2 times 4, is 8. We're going to combine those like terms in the middle. You're going to have 3x squared plus 7x, or sorry, not 7x, plus 10x. 4x plus 6x is going to be 10x plus that 8. Okay, our next example, we have two sets of brackets with a coefficient out front. So we're going to take the coefficient on our first bracket, we're going to distribute that in. Then we'll take the coefficient on our other bracket and we'll distribute that in as well, and combine any like terms we might have. So 2p times 7 is going to be 14p. 2p times a negative 3p is going to be a negative 6p squared. Remember, those both have an exponent of 1 on them. Now we'll distribute that negative 5. So we have a negative 5 times 3p, which is going to be a negative 15p. And a negative 5 times a negative 1 is a negative 5. So if we want to combine any like terms we have, you can see we have a 14p and a minus 15p here that we'll combine. I'm going to write my negative 6p squared first, because we like to, in algebraic expressions, write them in descending order by their exponent. So negative 6p squared. I'm going to combine my 14p minus 15p, and that's going to be a negative 1p. And then I have that minus 5 at the end to put on there. Okay, so we're going to just look at a word problem that relates to simplifying polynomial expressions to finish off the note for today. So we have a container is in the shape of rectangular prism. The width is 2 more than the height. So our width is represented right here in the picture. The length is 5 more than the height. That's represented there. And obviously x would be our height. So determine an expression for the volume of the container. So volume equals length times width times height. So we're going to sub in all those values. So in for length, I'm going to sub in x plus 5. And for width, we're going to substitute x plus 2. And then finally for my height, we have just x. So we'll start by foiling those binomials. So first, outer, inner, last. So x times x is x squared, 2 times x is 2x, 5 times x is 5x, and 5 times 2 is 10. And we still have that x outside we're going to have to deal with. But first we'll simplify any like terms we have, which are right in the middle. Of x squared plus 2x plus 5x is 7x, plus 10, and then times x. And then finally our last step is just going to be to distribute this x inside of our brackets, which I will finish that up over here. So we're going to have x times x squared, which is x to the power of 3, plus x times 7x is 7x squared, plus 10 times x is 10x. All right, so that is an expression for the volume of the container in standard form. And that is the note for today.